Good afternoon. Welcome to the final press conference of this 231st meeting of the American Astronomical Society. I'm Rick Fienberg, AAS Press Officer, and assisting me this afternoon by monitoring our webcast is my Deputy Press Officer, Inga Heyer, and then my AAS Media Fellow, Carrie Hensley, is in the back. She'll probably be helping with the mic at the end for Q&A. I'd like you all to please silence your cell phones. There are, I think, 4 press releases going out in connection with this briefing, and they're probably not in your inbox yet, but they'll be in your inbox shortly if you're on the AAS press list. And as I mentioned this morning, yesterday's press conference videos are now online in our online webcast archive. So I'll introduce the topic today and introduce all of our speakers and what they're going to tell us about. Then we'll have the 4 presentations in a row, and we'll follow that with questions and answers. And I think I can get right into it. So the theme of this briefing is from molecules to disks to planets. We're going to be hearing about things on small scales all the way up to planetary scales and even star cluster scales. There's evolution implied here, how we came to be, and I think you'll find it a very interesting collection of ground and space-based results. We're going to hear from 4 scientists. First will be Brett McGuire from the National Radio Astronomy Observatory. He'll be talking about Green Bank Telescope finds complex molecules in Taurus, and that's no bull. We're going to hear from Marc Kushner next from the NASA Goddard Space Flight Center. Rings and spirals can form by themselves in circumstellar disks. Then Jessie Christiansen from Caltech will talk about the discovery of a near-resonant chain of 5 Sub-Neptune planets found by citizen scientists. And finally, back to Hubble. Hubble searches for substellar companions in the Orion Nebula cluster by Giovanni Strampelli from the Space Telescope Science Institute. So with that, I'll turn it over to Brett. Oh, I should mention also that Brett's paper has appeared in Science just a few minutes ago. So there's no embargo on it anymore because Science's embargo has just lifted. So you don't need to worry about that.
All right, thanks, Rick. So I'm excited to tell you guys today about the detection of a new molecule in space, the aromatic molecule benzonitrile, for the first time using the Green Bank telescope. I want to point out to begin with a couple of folks from the key collaborators list that are in the audience today, Andrew Burkhart, Anthony Remijan, and Michael McCarthy. Draw special attention to Andrew Burkhart, who is giving a more detailed overview of these results in his dissertation presentation tomorrow, so I would encourage you all to go to that for more information. So to put this in a little bit of context, I want to go back in time about 30 years and discuss briefly a mystery called the unidentified infrared bands. These are a series of sharp emission features that are seen at infrared wavelengths towards predominantly warm, molecularly rich regions within our galaxy and also towards countless other galaxies in their interstellar media when we look outside our own. Now, these features individually cannot be assigned definitively to any single molecule. Instead, over the last 3 decades, a consensus has been reached in the community that this pattern can be reproduced in aggregate by a class of molecules called aromatic molecules, or specifically polycyclic aromatic hydrocarbons. And by observing these lines, their intensities, and their ubiquity in the universe, we've arrived at the conclusion that these molecules contain about 10% of all the carbon in the universe locked up into this class of molecules. So what is an aromatic molecule? Well, at its most basic, it's a ring of carbon atoms bonded together and sharing some extra electrons. So the ones that I put up on the board here are a collection of polycyclic aromatic hydrocarbons made up of benzene rings, probably the most common aromatic subunit in these. So that's a 6-membered ring there you can see in a circle, and you just piece them together like Legos to build up different molecules. Now in the lab here on Earth, the infrared spectra of these molecules, the signature, the fingerprint of them internally stretching and bending, is unique. Right? We can distinguish these one from another in laboratory spectra here on Earth. But there's so many different versions of these molecules in space, and they're all so similar that in aggregate, we can't identify one from the other. We can just get the overall fingerprint, and that is the unidentified infrared bands. So what we want to do is understand more about the chemistry, because this is a large sink of carbon. So it's important for us to know what carbon is going into these molecules and what carbon may be coming out of these molecules and seeding the basic molecules that might form biologically relevant species or be incorporated into dust grains as these grow even larger. So to do that, we want to observe the precursors to this, the single aromatic subunit, that 6-membered benzene ring. Now in the infrared, there's been a few reported detections of this, but it's very challenging, right? It falls within an atmospheric window, so we can't see it from the ground very easily, and it doesn't have a rotational spectrum that we can observe with radio telescopes because it's completely symmetric. So what we wanted to go after instead is a molecule that is chemically linked, benzonitrile. If you take a CN group, that CN radical there, which is common in the interstellar medium, and react it with benzene, you get benzonitrile. This is no longer symmetric, which means it has a rotational spectrum. That means that we can hopefully observe it using radio astronomy from the ground. Now the place that we chose to go looking for this is in the Taurus molecular cloud. It's a source called TMC1. We're going to use the Green Bank telescope. It's the most powerful radio telescope in the world for this kind of application. And the reason we're looking in this source is because it's cold, which is favorable for detecting these kinds of species. It's about 7 or 10 degrees above absolute zero. And it's known for containing large carbon molecules of similar composition to benzonitrile. So if we want to look for this, we need to know what spectrum we're expecting, what the spectral pattern is. So in Mike McCarthy's laboratory up at the CFA, we measured that spectrum. That's what's shown in red here. This is what we expect to see. And in white behind that is the spectrum that we observed with the GBT. You can see the match is quite good. In fact, in some of the cases, you can't even see the white data behind the red because it's such a good match. These are 4 of the lines that we saw. We saw another 5 additionally that are available in the figures in the paper. So this is a very good match and a very good identification of the molecule. Now by observing these lines, we can also get a handle on how much of this molecule is out there. And that means we can compare our expectations for the chemistry in this source using astrochemical models to what we see and determine whether or not we understand this chemistry well enough. So that's what we did. We used a chemical model called Nautilus. And what it does is it projects the abundance of different molecules over time. So that's the colored traces here. The age of TMC1, where we expect these abundances to fall, is at about 2 × 10⁵, and our observation of those abundances are the circles there. So I've just plotted a few of the relevant molecules. You can see the model does a fairly good job of reproducing CN up at the top in yellow, does a good job of reproducing some of the other large carbon molecules like HC5N and HC7N, and it actually gets close to benzonitrile. We produce about 25 to 33% of the benzonitrile that we observe using the model. And that means that this reaction, which is the one we put in the model to study, the benzene plus CN, is actually fairly good at making what we're seeing. Right? So there might be a few other production methods out there, or maybe we don't understand the chemistry of this reaction perfectly, but what it does say is that we're fairly confident that we can use benzonitrile as a proxy for this simple aromatic ring that we want to study. So to summarize, using the Green Bank telescope, we're reporting the first detection of benzonitrile. It happens to be the largest molecule ever detected by radio astronomy, and it's the first benzene ring containing molecule ever seen by radio astronomy. And as I've just shown you, this discovery is providing a direct chemical link to benzene and the polycyclic aromatic molecules that we think contain up to about 10% of all the carbon in the universe. Thanks.
Hi, I'm Marc Kushner from NASA Goddard Space Flight Center, and I stand before you today a scientist torn by conflict. I probably don't have to tell you about the beautiful images that Hubble and other telescopes have taken of circumstellar disks. Here are a few of my favorites. And they have all kinds of patterns in them, spirals and rings and arcs, and I've been struggling for years to try to understand these, figure out what's going on, what's causing them, and what they mean about, for example, the planetary systems that we know form in these kinds of disks. Well, it's tempting to suggest that the planets that we know are in the disks are creating all of the patterns we see. We know that planets can stir disks into spirals, and on other days, I've been caught advocating for this interpretation. But today I'm here with the opposite point of view. There's cool music playing. So here's one of my favorite disks. It's called HD 141569A, and you see it has arcs, and it has rings, and it has spirals. And are these caused by planets? Not so fast. Our latest supercomputer simulations, which were run on the NASA's Discover cluster using about 400,000 simulated particles embedded in gas, interacting with ultraviolet light from the star, show that even without a single planet, you can still make cool-looking spirals and rings and arcs. More details. Each grain acts in a way like a solar panel. So ultraviolet photons come in, and when they hit the grains, they kick off electrons, just like what happens in a solar panel, or actually in the CCD in your cell phone. They kick off electrons. The electrons then hit the gas molecules and heat them up. And in many disks, that's probably the main source of heat for the gas. Well, when this happens, imagine you had a clump of dust in the disk formed already. That's going to heat the nearby gas, and the hot gas is going to have higher pressure, and the higher pressure changes the nature of the gas drag on the grains, which has the effect of bringing in more grains, making the disk hotter and hotter and hotter. Lather, rinse, repeat, and you have what we call the photoelectric instability. So Vladimir Lehrer and I have been working on the photoelectric instability for several years, and here's one of our original models of it. It made cool-looking rings, narrow rings that do interesting oscillations and make clumps and so on. But what we've changed, what we did recently, is first we began working with a fantastic graduate student named Alex Richert, whose work this is, and we made a new supercomputer simulation where we've added radiation pressure and a range of grain sizes. And the range of grain sizes is important because each one experiences a relatively different amount of radiation pressure and gas drag. And when you put that all together, you're able to make rings and spirals and arcs in the distribution of dust. And apologies to my fellow planet hunters, no planet needed. Thanks, everyone.
Looking for your talk, hit the reset button. I'm on it. Okay. Hi, everybody. I'm very excited to be here today in front of a large group of you and in representing a large group of astronomers to present the first multi-planet system discovered entirely by citizen scientists. And gee, they found a good one. It's given us a lot of work for the last 8 months. The planets that they found are organized in this really interesting, unique, rare way, which I'm going to describe now. So our problem, this group of professional astronomers, our problem is that the NASA K2 mission is too successful. K2 uses the Kepler spacecraft to survey targets in the ecliptic, and we use those data to look for exoplanets. Now, every 3 months, the project releases something like 100 million new observations, which we need to download and calibrate and clean up and then put through our software and search for planets. The software finds thousands of signals that could potentially look even remotely like a planet, and then we have to sit through and go through them by eye and pull out all the really good planet candidates, and then we have to go to our large telescopes and sit and confirm, are these real planets or are they false positives? So basically, we were getting swamped. But the solution is citizen scientists. So Planet Hunters, which is an existing citizen science project, had already shown us that there was this huge crowd of people out there who were really excited to help us find exoplanets. Zooniverse is the public platform that hosts these projects. So using Zooniverse, we launched a new project called exoplanetexplorers.org, and the PI Ian Crossfield is in the audience back there. And what we asked the people to help us do was to go through those thousands of signals that the software had found and help us weed out the good-looking planets from the chaff. We were lucky enough that our project was actually launched on live primetime television in Australia. Hosts Brian Cox and Julia Zamiro, and also pictured here is Chris Lintott, who's in the back. In the first 48 hours after our project was launched, we had 10,000 volunteers make 2 million classifications, which we estimate saved us about 3 years' worth of work. And in those first 48 hours, they found over 180 good-looking new planet candidates, including the system that I'm announcing today, K2-138. So K2-138 is a very compact system of at least 5 sub-Neptune planets. Now, sub-Neptune means between the size of Earth and Neptune. And when I say very compact, the shortest period, the planet that's closest to the star, goes around the star every 2.5 days. The longest period planet that we found goes around the star every 12.8 days. So if you think about our solar system, Mercury is the closest planet to our sun, and it goes around every 88 days. So this is 5 planets going around their star less than 13 days. The star itself is an orange-yellow star, just a little bit smaller, a little bit cooler than our sun. So these planets, because they're all so close, are very hot. The closest in planet is 1300 Kelvin. So none of these are habitable, but it's still a very exciting system, and let me tell you why. Now we're looking at a top-down view of the system. The planet sizes here are correct relative to each other. So we think B, the innermost planet, the smallest one, is the only one that has a chance of being rocky. The outer planets are likely, they have large gas and volatile-rich envelopes like the outer planets in our solar system. And they've been scaled up relative to the size of the sun by a factor of 50. But what I want you to see in this picture is how the orbital spacing between the planets is smoothly increasing from the center out. And in fact, if you look at the period ratios, so if you divide each planet's period by the next planet out, they form this chain of near resonances. And the resonance that they are all in is the 3-to-2 resonance. That means that B goes around 3 times for every 2 times that C goes around. C goes around 3 times for every 2 times that D goes around, all the way out like clockwork. And this is the longest unbroken chain of these resonances that's been found so far. Now, an exact 3-to-2 resonance would be 1.5. And actually, if you actually do the math, they're all just outside the 3-to-2 resonance. I'm showing the period ratios here. And that's not unusual. We've seen before, looking at the Kepler multi-planet systems, that period ratios pile up outside the resonance. What's interesting here is that this unbroken sequence of resonances survives to today. Now, what that means is it gives us really important information about how these planets formed. So we know that 5 planets, nearly the size of Neptune, didn't form where we find them today. They formed further out and migrated in to be close to the star. And there's a few different competing mechanisms how that could have happened. Maybe they moved in smoothly through the disk, slowly together, nice family breakfast, or they fought with each other and interacted and kicked some out of the system and swapped places, and more like a Thanksgiving dinner. So, because we see them all in this really smooth configuration, we have to assume this is actually, a stable family unit. They all came in together in the disk. And that's really interesting because this is one of the few ways we have of probing what migration mechanism is working in these planets. Now, this is just a bit of fun, but I wanted to try and get across the idea of what a 3-to-2 resonance is, what it feels like, what it sounds like. And the 3-to-2 resonance is actually, in music, a perfect fifth interval. Now, the perfect fifth is the distance between the first 2 notes of Twinkle, Twinkle, Little Star. Twinkle, twinkle. That's a perfect fifth. The frequency of the ratio of the frequencies that I sang is 3-to-2. And perfect fifths are actually a foundational, fundamental interval in Western music. You can find them everywhere in music. Here I've highlighted in Pachelbel's canon just a few places that perfect fifths appear. Now, an exact 3-to-2 ratio, 1.5, doesn't actually sound as nice because the frequencies beat against each other. So musical instruments are often tuned just outside the 1.5 ratio, like the planets in our system. One of the people who thought about what the ideal perfect fifth sounded like was Johannes Kepler. He actually wrote a book called The Harmony of the World, where he wrote about math and music and astronomy and how they're all intertwined. And he defined the greater imperfect fifth, his ideal perfect fifth, as a ratio 1.518, which just happens to be the exact ratio of planets D to C in the system. So that's just a bit of fun, but I like to think about the fact that the citizen scientists have found us a real-life example of Kepler's harmony, a world where math and music and astronomy are all combined in this really nice way. So in summary, today I'm presenting the first multi-planet system discovered entirely by citizen scientists. It's this really interesting chain of resonances, which, like some of the other planet systems we know, like TRAPPIST-1, may represent a pristine chain. They all moved in together. They had no fights. It was an impossible family situation. And they are where we see them today. And just as part of today's press release, we wanted to announce on exoplanetexplorers.org, we just uploaded 55,000 new potential planetary signals, and we're really hoping people will go and look through them and find more systems as unique as K2138. Thank you very much.
Hello, everybody. Today I'm very excited to talk about the Substellar companion in the Orion Nebula cluster, a project that is being done at the Space Telescope under the supervision of Massimo Berto, that is here in this room today. So, for this project, we reprocessed the Wi-Fi C3 infrared data from the HST Treasury program. The target of this survey is the Orion Nebula, and it was done in 52 different visits, covering an area of the sky 1/6 of square degree, in two filters, the 130 and 130N. If we look at this plot, this shows two broadband filters, and we can clearly see that using these two kind of filters, we have a very big problem, because we can split the population from the Orion Nebula population from the Milky Way population. Why these two filters instead are very good? Because if we look at this plot shows different spectra for different kind of brown dwarf. The red line marks the position of the central wavelength for the filter 130, and the blue line marks the position for the central wavelength for the filter 139. The first one is on the continuum, and the second one is on the water in absorption. So we can use the color, so the difference between these two filters, to detect the presence of the water in this object. And this is what I'm showing in this plot. This is a color magnitude diagram with in gray the photometry from the Orion Nebula cluster. You can clearly see that below the 14 magnitude, we have a split in the population of the cluster. We have the object who shows water in absorption, so they has a color index, negative color index, and then we have the population from the background that doesn't show any water in absorption. This is just a schematic for the detector where each black dot marks the position of a source on the detector itself. Because the PSF can vary depending on the position of the detector, we decide to divide the detector in 100 quadrants and group together all the stars within the same quadrant, so they will have all more or less the same PSF function. Then for each star in the quadrant, we use all the other stars to build a model for the PSF, and then we use this model to perform the PSF subtraction on each star. These are just some output from our PSF subtraction routine. We can see that we have different cases. We have the first one, we just have one detection in both filters, but we can clearly see that for both filters, we can clearly see the companion. Then we have another example with two detections, so 2 rows, 4 detections, 4 different rows, and 5 detections. After we have the detection, we need to measure the magnitude of this object. To do that, we perform the 4-pixel photometry. So basically, we use a 4-pixel aperture on the centered on the candidate and on the primary. Why also on the primary? Because we already know the PSF for the primary, so from the difference between the PSF of the primary and the 4-pixel photometry, we can easily find the conversion factor between the PSF photometry and the 4-pixel photometry to apply to the photometry of the companion. Once we have the photometry, we can plot over the previous CMD the position for our companion. So again, we have in gray the PSF for the PSF photometry for the cluster, and the black and blue cross marks the position for the primary and the companion with the relative error bars. The green dotted line join together the binary system. With this plot, I want just to summarize our result. So we have on both axes, we have on the x-axis the mass of the primary, and on the y-axis the mass of the companion. And then this plot can be split in 9 different areas, depending on the mass of the primary and the companion. So we have in the left upper corner, we have the star planet mass. In the center corner, in the center part, we have the brown dwarf mass. And in the lower right corner, for example, we have the planet star mass. For reference are also shown 3 diagonal lines, the 3 dotted line, where is shown the position where the mass of the primary is equal to the mass of the companion. The mass of the primary is equal to 10 times the mass of the companion. The mass of the primary is equal to 100 times the mass of the companion. As you can see, most of our candidate lies very close to the line where the mass of the primary is equal to 10 times the mass of the companion, with some scatter, of course. But we can also use this plot to try to understand the nature of this object. So, as I said before, we have 2 star-star candidate binary systems. We have several brown dwarf star candidate system, and one is just shown as an example. We also have one brown dwarf binary system, and we also have this very peculiar object, the last one. This looks like a planet system without any star close to it. Thank you very much.
Well, we've played gravitational wave chirps and fast radio bursts and some other things, but I don't think we've ever had anybody sing in a press conference before. So thank you. That's a new first. All right, we're going to go to Q&A. Inga is monitoring the webcast. Who's got the roving mic? Carrie? Okay, great. So if you have a question here in the room, raise your hand and wait for the microphone. Tell us who you are and who you write for. And then if you're on the webcast, please queue up your questions using the text chat. Okay, questions in the room. We'll start down here with Camille.
Hi, sorry, I have a croak for a voice today. This question is from Mark. Are you at the point where you can say if there are any specific traits of a disk that would be more likely to be a no planet versus, well, if I see this kind of feature, it's more likely to be a planet that's involved in the disk features?
That's a good question. So, sort of a smoking gun where you see this and you say, well, that's probably got to be a planet. It can't be explained by anything else. No, at the moment, we're still. Each time we run the simulations, we discover yet another kind of pattern that you can reproduce with instability. Actually, I take that back. So we're only modeling disks that have both gas and dust. So if you don't have the gas, it's a different game. And then I would say that there are signatures which I do think would strongly be suggestive of planets. And one of them that's been around is the eccentric ring. So if you have a narrow ring of planetesimals, and it's not centered on the star, like the kind that you see around the star Fomalhaut. The putative plan in that system is still up for debate, but I still think that pattern is a strong indicator of planets in that relatively gasless system. Thanks.
Okay, Ethan.
Hi, this is Ethan Siegel from Starts With a Bang. This question's for Jessie. You've been living in the US a long time if you're making Thanksgiving references. That's not the question. So you have about 287,000 stars from K2 that need analysis, and you're identifying the ones that have been flagged with multiple transits, et cetera. So I guess I have 2 questions. One is, how many hours, person hours from citizen scientists do you estimate you need to actually go through all of these? And two is, how are we doing with the multiple transit systems? How many of those do we have?
That's a really great question, or a really great set of questions, Ethan. So to answer the first question, we just uploaded 55,000 new potential transit signals from 3 campaigns, and there are 15 campaigns, so there's something like 250,000 transit signals to go through. We'd like each of them to be looked at least 10 times. And part of the trade-off you make when you're using citizen scientists is they don't have the same expertise. Like when I was a grad student, I looked at 80,000 light curves, but I can't expect that everybody's done that. So we like them to be looked at 10 times so that we get a good statistical sample, and we're not just getting, junk in, junk out sort of thing. So let's say 2.5 million, and we have 2 million classifications, and I would guess that they looked at them, for a few minutes each. So 2 million times a few minutes, a lot of people hours is the answer. I'm not going to do the math right here. In terms of multi-planet systems, we actually have spent so much time trying to disentangle K2-138. So originally, it had 4 planets, then it had 5 planets. And what I didn't talk about is there is a 6th candidate further out, which we need to follow up. So this is the way of science, right? Like you get really deep in a signal. We have that whole rest of that list of 180 things that we want to go through and pick out the good stuff. And now we have 55,000 more light curves for them to look at. So we're getting swamped by the citizen scientists now. It's a good place to be. Oh, actually, that's fantastic. So it's at 42 days, which if you keep going with the resonant chain, you skip 19 days and you skip 27 days, but you end up at about 43 days. So that's a really tantalizing clue that maybe we're missing more planets in the system. Like if this chain continues, there's a gap. So that's exciting.
Okay, come around here to Andy.
Andrew Frackner, I guess OpenStax textbooks, and also for Jessie. You started to say that there was already a citizen science project, but then you guys had a different one. So say a few words about what the problem was with the first one or the difference was.
Sure.
And then second of all, how much training does each of your citizen scientists get before you let them loose on the data?
Great questions. So the first citizen science exoplanet project was called Planet Hunters. Now, the goal with Planet Hunters was for the citizen scientists to find single events in the light curves that the software weren't picking up. So the Kepler software was designed to need 3 transits. You need 3 transits to have a secure period. But there are many light curves that have 1 or only 2 transit events in them, or light curves that the star is doing so much other interesting stuff that the software never had a chance of finding the little signals. But that's where people are perfect. You just put that light curve in front of someone, they see that 1 signal, they see those 2, or within all of the mess, they see a transit. Humans are great at pattern recognition. So Planet Hunters was designed for them to look carefully at the light curves and find events that we weren't finding. What Exoplanet Explorers is doing is moving to the next step and saying, we've run the software, we found all of the periodic events, but now we've got too many of those to look through. So they're actually helping us do the vetting, where we look at all of the potential candidates that the software's found and say, this is junk, this is real, this is junk, this is real. So that's the difference between the 2 projects. In terms of the amount of training, we have a few examples of the different types of things that can look real and can look like junk that we show them beforehand, and there's a minimal bit of text, but really we just kind of launch into it. You get a feel for it as you go fairly quickly. We want the overhead to be small for people to get started. We want them playing with real data as quickly as possible. Instant gratification.
Do we have any webcast questions? Okay, we'll go to those then.
We have a question from Rick Lovett, freelance, also for Jessie. What is the significance of the fact that the resonances aren't perfect? Especially, what is the significance of matching Kepler's perfect intervals? Does this have something to do with beats messing up the resonance with planets?
That's really great. So we see that these resonances pile up outside of the exact resonance, and the current theory is that dissipation in the disk, so planets would like to be just outside the resonance because it is hard to stay in the resonance. So they dissipate a bit of energy and end up just outside. It's tidal dissipation, basically. And I believe that that is correct, that it's actually difficult for them to stay in a resonance because it actually gets unstable. The libration frequency it would send them unstable. So they like to pile up just outside. So I think Rick has it correct.
Nothing else online at the moment? Okay, more questions here? Okay, we have one in the back. Please remember to identify yourself.
Hi, my name is Ibrahim. I'm an undergraduate from Skidmore College, and I have a question for Brett, Dr. Brett. I was wondering, when you said the benzonitrile, the discovery that there are carbon atoms, and then something that I was wondering was, would it help in figuring out the evolution of, I don't know, stars, or perhaps how would it fit into the larger picture of figuring out how the universe, expanded, and is there some sort of significance in that regard? Thank you.
Sure, that's a good question. So one of the cool things about the larger aromatic molecules, so you take the benzene ring in the benzonitrile and build it up to those larger Lego blocks that you've clicked together, is that if you get them large enough, they can be the seeds for interstellar dust. Right? And this is the mass that we heard about forming eventually rings and gaps or planets in some of these systems, right? So that's a way that the carbon from these class of molecules can be incorporated directly into forming planetary systems and can infall that way as they grow bigger and bigger and form that dust. From the other side of the scale, there's a lot of carbon and hydrogen in them, and that carbon is essential for life. So if you take these molecules and you expose them to harsh radiation from a newborn star, for instance, you can also break them back down into their constituent components and use those as seeds for making more biologically relevant molecules once you're in these chemically reactive environments. So things like amino acids and sugars that we see in meteorites, but we haven't yet detected in the gas phase in the interstellar medium. Those can be formed from the pieces of these aromatic molecules that have been blown up.
Any other questions in the room? Okay, take one down here in the front. I have a question too.
Hi, so my question is for Giovanni. I was wondering if you found a lot of brown dwarfs in your sample. Was this unexpected, or was this more or less than the fraction of brown dwarfs that you expected to be in this stellar population?
Well, the fraction of brown dwarfs that we found was the fraction expected, yes.
Okay, so what was particularly, what will you do next with this information now that you've been able to actually spot these companions and understand the statistics? What will you do with this information next? Yes.
Well, the next step will be, now that we have the detection, we can check the model, we can say. We can try to test the model to see if they can reproduce the same detection that we have. So the same number of brown dwarf, planetary system, star planet that we can see in our survey. And then you can select which theory better represent our detection.
Okay, thank you very much.
Welcome.
And my question was also for you, Giovanni. I was particularly intrigued by your comment that seemed to just kind of fly by unnoticed, that you found a couple of planets that seemed to be together without a star. So I guess I have a couple of questions. One is, how robust are your distinctions between planets and brown dwarfs and stars? And then if you are truly confident that you have a double planet without a brown dwarf or a star that you can detect, what might that imply for the kinds of pathways to planet formation that are happening in the Orion Nebula?
Okay, so to define what is a planet or what is brown dwarf, we use a mass definition. So everything below the 13 Jupiter mass, we define planet in our project. Now, to evaluate the mass, we use the photometry. So the photometry has error. So more you go down with the photometry, bigger are the errors. So for this planet, we have 20, 22 magnitude, so the error bar are very big in this case. So we can be 100% sure, not right now, that that's actually a planet and maybe not a brown dwarf that within the error bars, you can see it as a planet. But maybe with a future follow-up, we can improve our understanding, so James Webb for the future. And about the second question, I don't know if Massimo wants to add something to answer the second question.
If you do, let's bring the mic over. Sorry, Massimo, right here.
I would say that, so the big problem, we call planets something that may not be a planet because it's just a very, very low mass object that is planetary mass, the way with this definition. The fact that if we find a pair, it means that even to these very low masses, you may form binary systems following the same type of process that you have with larger mass through brown dwarfs to stars, etc. So you can propagate the system that forms a binary to very low masses, and therefore is the fact that these systems exist single or binaries. You may form planetary mass objects like stars. Instead, the other idea is that you need a disk, and then there is some kick, some ejection that is needed. How many we find bounded around the star, if we find binaries, if we find how many isolated, it's all pieces of the puzzle that may be reconstructed to disentangle if these very low mass objects need a star to form, which means need a disk, or they may form just like stars out of cores in the ISM.
But this is actually an area of very active work, right? I mean,
absolutely, absolutely. The point is that at these masses, the theorists don't have enough statistics because the models can easily predict star, planet, ejection, etc. But we really miss the data. So this is the first time that we go so faint in this really uncharted territory that will be fantastic for James Webb, in fact, because Webb has many more filters in these molecular bands, goes much deeper, has a wider area. So this is like an exploration of things that will explode in the next couple of years, I think.
But you could be seeing rogue planets information, basically, or something like that.
Yes, and in fact, one of the real problems for the future is how do we assume that we finally say, okay, this is a 12 Jupiter masses, so it's a planetary mass object in the field. Is it formed like a star or formed like a planet that has been kicked out? To understand what are the diagnostic in the spectra that tell you if it formed in a disk or which has some sort of aggregation, as a sort of, the entropy of the system that grew up in a different way that is formed out of a core of interstellar medium. What are the signatures in the spectroscopy that we will look for to disentangle the two scenarios? That's another problem that is very open.
I think we have a question right behind you.
Steve Marin, freelancing. I'm sure there's a good answer to this, but it's not clear to the uninitiated. If you're, for the planet, supposed planets, where the photometry is so weak, then whatever information you use on the colors or spectral information so you can get a mass must also be, I suppose, even weaker. So how can you put some confidence level or factor on that these are not some other brighter objects at a much greater distance?
So first of all, this is still a work in progress, so we still have to do a lot of study about this object to understand their true nature. The most strong constraint that we can put is the color. This planetary binary system has a negative color index. So it looks like it's showing water in absorption. And this makes us confident to say that it belongs to the Orion Nebula cluster, not to the background star. But still, we have to make more follow-up for this object before we can make any claim.
I would add their number is extravagantly high with respect. The number is too high for what you expect from the background contamination. We see the Milky Way down there. We can estimate. We have binaries there. And the number of binaries is fully compatible with what we expect from the random distribution of the field. You have 3, 4 sources that must be so close when you have so many stars. But the number of binaries that we see on the left side of the plot in the water absorption is crazy high. So there is a systematic, we may be wrong in one case or two, but they are there. We need to be sure which one is which. We need spectroscopy and further data. But there is a population of planetary masses, objects there that we are digging out.
Okay, any further questions here in the room? How about online? Nothing? All right. Well, we're allowed to quit a little bit early. So I want to thank all the speakers again for your very fine presentations and singing. And I want to thank the public information officers who worked with us to put this briefing together and who prepared all the press releases that are now sitting in the inboxes of the reporters. A couple of quick announcements. If you are going to the press dinner this evening, again, that's at 7 o'clock at Rosa Mexicano. If you'd like to meet with us and walk over together, we're going to meet in the hotel lobby out by the main entrance. And then if you're going on the press tour tomorrow to the Space Telescope Science Institute, check the email that you got from Christine Pulliam giving you instructions for where and when to meet. We're being picked up in the morning at 8 at the bus loop, and you'll have nice detailed instructions in your email. If you don't find that email, please get in touch either with me or with Christine. So I always like to look ahead to the next press conference, which in this case is on Monday, June 4th in Denver, Colorado. I don't know the topic yet, but I'm sure it'll be something exciting, and I look forward to seeing many of you there. So thanks again for your attendance and your attention, and have an enjoyable rest of the meeting. This is the last press conference for this meeting because many of us will be at the Space Telescope tomorrow. So thanks again, everybody. Bye-bye. Thanks.